guys, sorry it's been a little bit since I did a video. I've had several surgeries on my eyes. I am seeing much better now. They're saying this one's still healing from the original damage, and I have some different vision I'm really having to get used to. But in today's video, I want to talk about revability. Now, yeah, that's a made-up word. I made it up back in the 80s. I had a problem where when I first started building engines, one engine seemed to do better than the other. And so I came up with a term called revability. The ability of the engine to change RPM. And basically, I found that certain engines would rev better than other engines. Now, I used that term for probably 20 years, up to about 2000 or so, and then I quit using it. I basically just started saying, we have to get things right. And I had learned a lot about how the internal combustion engine works. Now, one of the things that has come up recently is that same basic idea. And I remembered the term from way back that I was using. And the idea was that the dyno isn't going to show you everything. And this is certainly true. I've told you before, especially for like driving characteristics and a street engine and how well it's going to behave, the dyno's not a good tool for that unless you go to a hub dyno where you can adjust the load, make it more like driven while you're looking at the parameters and can tweak the engine. But a regular engine dyno is wide open throttle and usually doesn't even go that low in RPM, though we have run ours at 1,000 to 5 before without any real problem. Anybody that tells you a dyno can't do low RPM, it's not the dyno that has the problem, it's the engine that has a problem. If you build an engine and you can't load it in at 2,000 RPM because it's just not making any power down there, and then you convince yourself, well, I can run from 4 to 7, and that's really how it works. And the dyno is the problem. Now, the dyno's not the problem, the engine is the problem. And then you convince yourself that 4,000 RPM is low RPM. And you say, you know, how great a torque am I doing at low RPM? Well, 4,000 is not low, 4,000 is mid. And I even saw David Vissard one time on one of his motors that made really good torque. It was a big block race motor, good torque motor, big cam. But it made it at like 5,200 RPM. And he said, well, that'd make a good RV motor with that kind of torque. Not at 52. Let's make sure that it's correct. Well, revability is kind of that same thinking. Is on a dyno, when you run the dyno is actually controlling the rate that the engine goes up in RPM. And you can set that, 150, 300, 600, which is fairly normal, 1200, which is kind of fast, 300 is not a bad number, it's a little slower. Courtney did the 150 rate on me at one time, and man, that's a long pull. But you control the rate, and the computer controls how much load the engine sees in order to keep it at that rate. Because of that, you don't actually get to see how the engine revs. And so the dyno isn't really showing you this revability. Yeah, I know, it's a fake word. But you need to see that engines can be different. Even on the dyno, one of the things that I like to do is listen to the engine. I much prefer when Mario or somebody else is driving the dyno and I can just stand there and listen. And that's worked real well with Courtney originally because he loved to drive. And Mario was kind of the same way. Unfortunately now I'm going to have to drive the dyno and listen at the same time. But I like listening to it because you're listening to several things. Your ears, when it comes to engine, your ears are important. Your ears are important for what's happening on a flow bench. Your ears are important for what's happening on the dyno. Not just the numbers. You can get numbers. But you also have to listen to what's going on. How well the engine loads in. When you run the dyno, you set an RPM, you turn on the sequence, you load the dyno to wide open throttle. Once the engine stabilizes, now with some dynos, once it stabilizes, it automatically goes. With our dyno, you have to give it full throttle, wait for it a minute not a minute, a few seconds, to stabilize. Once it seems pretty stable, you hit the run and it does its sweep. And like I said, it controls the rate at which that sweep happens. How many RPM a second, okay? And so you can listen to how it does on that load-in. You can sometimes go to a lower RPM and load in to see how it does, because that load in will tell you how well the engine may behave out on the street and driving. But the rate, like I said, is controlled by the computer. So if you have an engine that really wants to rev and one that doesn't, they're both going to run at the same rate. So what you're actually listening for is how well it's struggling. Some engines, when you do the sweep on the dyno, are clean and clear and crisp, and they just go. That's a good engine. Some of them will even make the same number, but when you listen to it, it will struggle. And it's not real even, and the computer sometimes even seems to momentarily fluctuate the load a little bit in order to maintain the RPM. It's not as clean a run. And that's the kind of stuff I'm listening to. Now, some of that certainly can be tuned. Timing, how well the carb's doing, some of that. But there are also some inherent designs in the engine that control how well it revs. And we're not just talking free revving, you in your driveway going wow, wow, wow. We're talking about under load, how well it behaves. And like I said, I'm not even talking about a number. It could make the number. It could make the same basic curve, but it can behave differently. And that's the piece we're kind of talking about today. Now, what I first learned all those decades ago was the exhaust side has a real effect on what I'm talking about. And anybody that's gone from cast iron manifolds to headers has seen this. You throw on a new exhaust system, headers, maybe a different set of pipes, maybe going from single to dual, better muffler, get a different sound, and Then you go for a drive. And you're like, wow, this really made a difference. Now on the dyno, that may have only been, 15, maybe 20 horsepower. Not a huge difference. Yet when you're driving it, it feels way different. It seems to rev way better. And that's because you're affecting the breathing. And that's what I want to talk about today. The revability of a motor has a lot to do with how it breathes. Now, we're really good about putting big heads on motors, sometimes bigger than what the engine should actually have, and costing you low end power. And certainly if the engine is struggling, it will, with airspeed, it will not rev as well. And you can hear this even on the dyno sometimes, and see it on the graph, is you load it in, it kind of stabilizes, it starts to go, it struggles, and then you hit a certain RPM, which may be 3,000, 3,500, and it suddenly clears up and just goes. And so your airspeed got up to where things started functioning correctly and the engine started working better. And this is why some guys won't test that low, is they don't want you to see or hear what's going on in those lower RPMs. And then they'll try and convince you that, 4 to 7 is fine. Well, 4 to 7 is fine in a drag racing application, but certainly not on the street, and even in some circle track, you may need a wider power band than that. You need to make the power band that you're working on better. And this is why some guys are now pushing more for, let's look at average power. But the same guy that's only testing from 4 to 7 will then use that and say, well, look, my average horsepower is really good. Well, yeah, your average horsepower from 4 to 7. What's it like from 25 up? The engine, especially on the street, needs to be flexible, and you need to have a slightly decent power bank. 3,000 RPM is minimal. If you're down to 2,000 RPM of workable, that's getting kind of peaky. Most engines, you should be able to get a fairly decent band of about 4,000 RPM. And in most of this series, I've talked about that. Watching your overlap, watching some of your events in order to help that out. But at the moment, we're not even really talking about power band. I'm just talking about the ability of the engine to rev. And what that is really how easy is it for that engine to breathe. Because you have to draw in the air. You're creating a vacuum. If you're creating a much bigger vacuum than you should, then you are using up work in the engine to draw in that air. And the same with the exhaust. If you're having to push the exhaust out, you're wasting energy trying to make that happen, and you're kind of like bottling up the engine, and so it doesn't run well. And that's why putting a better exhaust on a car makes it seem way better than the power you gain, is because you freed up the exhaust and it revs better. Now, that's why a lot of times I'm pushing that exhaust opening point. I'm trying to get that blowdown to happen to free up that power. That mostly will show up on a dyno up there as carryover. And you can do this with an engine, even if you are flow limited. say you have certain rules and you can only run so much cylinder head, but you need more out of it. Well, what you're going to do is not really make peak happen later because you're flow limited, but you're going to make the carryover do way better. How much power you make past peak, how well you carry that same power up to a higher RPM. And this can show up as a better curve. And the engine will behave better and you have a wider power band. And a lot of that has to do with your blowdown point. And so you have to watch your events. Now, like I said, if we're working on a street vehicle, 2,000 to 6, that's our 4,000 RPM band. Well, you're working down here. Then you really got to kind of watch overlap. Now, if you're working on a drag racing motor, those are easy. You can throw a lot of cam at it. Your events down here are going to spread way out just because the cam's bigger. You're going to wind up with overlap, but if you're doing one of those engines, you may only need 4,000 to 8. And so down here doesn't matter. You don't care about overlap. But the overlap isn't really helping you. It's damaging that power down here. But it may gain you a little bit with a tuned exhaust, which we talked about before. That tuned exhaust is going to make the engine feel better because its ability to cycle air is going to be just a little bit better. That's why when you listen to some of these full-out race motors, or you go to a NASCAR race or a cup race and you listen to them, they are just clean. Now some of it is they're really big cams, but some of it is the breathing is really decent. And a lot of that has to do with the cam events have been fine-tuned, certainly in the RPM that they're working in. You know, one of those kind of engines, you may be working 5 to 9, you know, maybe even 55 to 95. And so you're way up there in the RPM band. But you need to address that issue well enough that the engine doesn't feel bottled up. And that's why a lot of times you find me pushing events, especially the closing event down here. I want that horsepower. I want that volumetric efficiency. I will make the airspeed work so that I can use that, because that's the key to making this work. If you wind up having to pull that back to do better, that's because you have an airspeed problem. That airspeed problem means things are not sized correctly. And that's why I went from calling it Revability to just making sure things are correct. Because the correct size port will help you. Now, a big port will help you up here. It sounds better. You can get that carryover, you can get that power up there, the motor sounds clean, because you've got a big head, and by the time you get up there, the airspeed's okay, and you have fairly decent breathing. If you have extra breathing, more than what you need by the CFM demand formula, for the RPM you're working in, well then you can get away with less cam, and the motor tends to rev better. That revability is there. If you're not, if you start sizing things correctly, or you're limited because class rules say you have to run this head, that's all you've got. And even if you've tweaked it a little bit, shop peened it so they can't tell, it's still limited. That head can only do so much. You might have given it a better valve job. You might have picked up a few CFM. All of that helps. But what you're really stuck with is the camshaft. And two things are really important to get that revability. That ability for the motor to just go. And that has to do with the initial breathing at peak piston speed and your blow down or your exhaust getting out of the engine. I have told you before, this is the first most important thing. Without this, this doesn't work. Otherwise, you're just playing catch up and you get weird results. You add more cam and it just doesn't work. If you don't have the airspeed right, the cross section correct, this won't work when you get up to really big cams. You stall out at a ZL1 because you don't have the airspeed to carry more. So sizing is important, but then when sizing is important, this fill becomes more important. So you have to pay attention to how much you're getting at peak piston speed or that 75 degrees or so after TDC. If you're trying to run a little cam, you're working from, you think 2 to 5, say. That's my power band. Or 2 to 6, maybe even. Maybe a street motor, you may be working 1 to 5. You know, like we did with the 355. But you need to pay attention to how much flow you have here. If you are limited in flow, you've got to try and get this open now. You are going to have to be over here. Now, if you just pump in a bunch of duration, or you tighten up the load centers, suddenly you've pumped in a bunch of overlap, and that may be detrimental. So you may have to do what, if you watch what I do, this is why. I may spread the load center and then twist the cam into an advance to get rid of some of that overlap. Open that exhaust valve sooner and get a better fill at that peak piston speed, because that's what makes the motor want to go. This is your initial fill, and that's the feeling of the motor just going, because as the piston comes down, this is where it's initially drawing from. This is inertia ramp. This is after the piston is down and coming back up, and you're using airspeed to fill the cylinder down here. So that becomes about cross-section, airspeed, and inertia ramp. That initial feeling, that revability, the ability of the motor to just take off and go, is about fill at that peak piston speed. And the more restricted you are, the better exposure you need here. Now you can take 74 degrees, 75 degrees, wherever your stroke actually puts peak piston velocity, and you can take that piston speed and calculate that instantaneous air that's needed. And that's just a minute moment in time. I need this much flow. Well, in my experience, you almost can't get there. You're always trying to open the valve earlier. And I'm always trying to open the valve earlier and limit my overlap, which is a difficult thing, because you've got piston to valve clearance, especially on a performance motor where you're trying to get compression out of it, and especially on a performance motor you're trying to get compression out of, and you have a certain head you have to run. Well, you are fighting to have room for the valve to open. A lot of times, it's not what I want to be open here. It's what I'm allowed to be open here, because I just don't have the room to open it any better. And that's where the problem sometimes occurs, is you need to get the best exposure you can at this point in the cycle. If you try and say, well, it's a limited class and they're trying to keep the RPM down, and some of them even limit the RPM. I have seen places that say, okay, well, you're going to run a 5,500 RPM chip. Now, the idea of all this was to keep the builds down to a minimum. Your build is going to be more basic. But as a builder, we have to see if we can make the best we can with those limitations. And so, if you are limited in RPM, you may say, well, I'm going to run a smaller cam. I'm going to reduce that overlap so that my power down here is good. But that doesn't give you a good fill, and you can make a slug of a motor. A lot of my early ones back in the 80s, which is what coined this term, had that problem. I mean, you got to remember, we didn't have all the head choices we have today. So I didn't have the way high breathing ability of some of the heads that exist today. And I had to try and figure out why one engine did really well and another not so much so. And I had one Firebird that ran perfect. There was nothing wrong with it, but it was a complete dog. And that's what started making me go, why? Why is this one just terrible? It has no power. It doesn't want to go. It's just a dog. And that's when I got the flow bench and started looking into breathing. And later on, I started learning about camshafts. And another example of this was when I first got into Cadillacs. Now, I've told you before, the Monte Carlo that I built was using the Cadillac engine I had built for an Eldorado. Now, when I built that engine, I built it completely stock. And it was fun. I mean, it had a new timing chain, had a new cam in it, valve job, did great, new springs, completely stock. I moved that from the Eldo, which drove just fine. A big car, 6,800 pound convertible, low RPM, no gear, just cruising around. Motor was perfect. I put it into a Monte Carlo. Now the Monte Carlo I was building, I built like I build small blocks. 390 rear gear, a Turbo 400, which has a 248 first gear, a 2500 stall converter. I wound up having to build headers for the Cadillac just to fit the chassis because the cast iron manifolds didn't fit. Put it in dual exhaust, built it like you'd build a muscle car. You know, it's got a 10-to-1 first gear ratio between the rear and the first gear. And so you got a lot of multiplication. And what I wound up building was a tractor. The engine, I didn't understand at the time. Peak torque on the engine happens at like 2,800 RPM. And the converter was 2,500 stall. And the gear ratio in first, between first gear 248 and rear gear 390, was almost 10-to-1. Now, the Cadillac engine had 500 plus foot-pounds of torque. So that meant I had like 5,000 foot-pounds of torque at the axle and no RPM. I mean, because I'm at 2,800 RPM, I'm barely going. And I've got all this torque at the axle. It's a tractor. And that's when I realized I'd kind of made a mistake. Now, I wound up having to drive the car for a while that way before I got around to it. And I told you the story before. I called up Ed Escuderian, tried to get a different cam, and what I got wasn't right. But it's not his fault. He's thinking Cadillac, big car, low RPM, trying to not overcam it, trying not to give it too much cam. I call up Cadillac Motorsports Development, Larry Kruzak, and I ask for a cam and I tell him what I've got. Well, I don't get anything that's much different. And the problem is, He was building Cadillacs for trucks. That was his primary thing. Neither one of these guys were thinking muscle car. They were thinking low RPM. And that's not what I was looking for. So eventually, I did what any hot rodder does. I went to the crank catalog. I went to the bottom of the list, the biggest cam they offer. And I put that in the motor. Now, I had started learning some about cams at that point, and so I did put it in a little differently than most people. I put it in 8 degrees advanced. That's because at the time, I didn't completely understand inertia ramp, but I knew this was important. And that freed up the motor. Between having an earlier exhaust and a better fill at peak piston speed, that engine took off. Plus, I wound up with carryover. And this is where I met Courtney. His first words out of his mouth were, "What RPM are you shifting at?" I was shifting at like 6, 6.2, 6.5, depending on how long I hung on. And he's like, "It doesn't make any power up there." Well, technically, when I went to the dyno, and I have the dyno sheet, it was making power up there. But it wasn't peaking there. It was still peaking at like 5,000 RPM. Because even though I'd done a little port work, I had my flow bench at this point, I had a little bigger valve, I had a little bigger cam, I had a little better breathing. What I had was really good carryover. And that engine carried almost flat past 5,000 to 6. And that allowed me to rev better. The motor just breathed well. And a lot of that had to do with these two events. And remember, I was concentrating on this event. I was trying to get it as open as I could to make that happen. And it worked. And that's when I started learning what it actually takes to make an engine just go. And so this video, I just want you to keep thinking, not everything is about peak power. Some things we do is about other places in the power band. The ability of the motor to run well can really have to do with these other events, not just peak power. Peak power is inertia ramp. But these other events do affect how the engine's going to run. And it's not always about that peak power. It may be about your cross-sectional area and your low end power, making sure you carry that low end, making sure you have that flat torque curve, making sure you have maybe that carryover past your peak, because you are limited either by the basic design of the engine, like the Cadillac, or by rules in some sort of racing program that you're trying to do. And when you start thinking about those, think about these events and what you're doing in order to get that motor to be good and just go. And I'm hoping this kind of explains some of my thinking when we've chosen cams in the past and why I do what I do. These things matter, and if you want to call it revability, call it. I gave up using that word 20 years ago. But the basic idea of an engine that is free breathing enough that it's able to change RPM. And that's the whole goal of this particular video. And I hope this helped you design a better engine and make it do what you want it to do, and why other events in the camshaft are important. Adding overlap without trying to make real use of it, of a tuned exhaust, is a bad idea. But you want that early opening because you want that better exposure. Same on the exhaust. You can push this out. This is your blowdown. It'll make it louder, but it'll make it rev better. It's about your breathing. It's about the piston not having to push out that exhaust. It's about the piston not having to pull so hard to get that air to come in. It's not always about how big the cylinder head is, because the cylinder head gets too big, your airspeed drops, and your power down here becomes a problem, and next thing you know, it only works from 4 to 6, and that's a bad thing. So I hope this one helps you. Like I said, it kind of came up. I think I did a decent job of explaining it. If not, leave something in the comments. Like I said in this, the dyno kind of lies to you. You got to listen to it. It's not all about the numbers. But if we need to do some videos about how the dyno actually works to help you understand better what you see, what you get on the dyno, let me know in the comments, because I think we can do a video on that and talk about correction factors and whether or not people are lying to you on their dyno, how they're calibrated, how they basically behave, and what you should expect to see, because that helps you understand the actual information you're getting. So if you want that, let me know. Tell me in the comments. Until then, have a good day. I hope your projects are going well. I'm happy to be able to start seeing better. We still got some more work to do. This one's still kind of healing up from original damage. But I'm hoping to get better and better and get into getting some more of this work done. I'm a little more overloaded these days. Since Mario left, I've got more to do. But we're going to try and keep forging ahead. We'll talk to you later, and have a good day.